20th lecture being delivered on 22nd February 1994, and the topic is AC circuit analysis. Before we start the topic proper, I wanted to give a bit more physical interpretation of the impulse function. You recall that yesterday we were trying to find out the current response in this circuit when the applied voltage is an impulse. Let this impulse be capital A delta t, where capital A delta t is the limit of a pulse of height capital V and duration capital T, so that capital A is equal to Vt and the excitation is A delta t when capital T tends to 0 and capital V tends to infinity, in such a manner that Vt is always equal to A. Vt is always equal to A. I want to give a physical interpretation. We argued that I of 0 minus is equal to 0, but I of 0 plus is not equal to 0, and we argued that it must be equal to A by L. This was done from the argument that the total drop occurs across capital L, and therefore from 0 minus to 0 plus the current in the circuit, current in the inductance shall be 1 by L integral of the voltage with respect to time, and integral of A delta t from 0 minus to 0 plus is simply equal to capital A, and therefore the current was capital A by L. I want to give you a bit of physical interpretation of this by approaching the problem from that of a pulse response and allowing capital T to go to 0. You see, if I apply a step like this, a step which rises from 0 to capital V at t equal to 0 and which remains a constant, the current I of t in the circuit shall be simply V by R, then the initial current is 0, and therefore it would be 1 minus e to the minus RT by L. Agreed? This will be the current when a step is applied. The current gradually builds up from the value 0 to the value V by R. Now if we apply the pulse, that is another negative step at small t equal to capital T, the response to that shall be V by R minus V by R, 1 minus e to the power minus R t minus capital T divided by L. Alright, and the total current response would be equal to this multiplied by U of t, because it occurs for t greater than or equal to 0, and this quantity shall be multiplied by U of t minus capital T. Agreed? This is by inspection that the pulse has been resolved into two steps, one positive, one negative. Positive one occurring at small t equal to 0, negative one occurring at small t equal to capital T, and therefore it is the difference, it is the superposition of these two responses. Now if I plot the current I versus T, if I plot the current I versus T, then the current rises like this, and we would have gone to, let us say, V by R, would have gone to V by R if it was allowed to, but at at small t equal to capital T, the negative pulse, negative step comes into effect, and therefore the current gradually diminishes. It diminishes like this, all right. And you see the the maximum response would be simply given by V by R 1 minus R capital T divided by L. Is that okay? I beg your pardon. V by R 1 minus e to the minus R capital T by L. All right. The point is, now when capital T goes to 0, tends to 0, obviously what will happen is that this rise shall be limited from 0 minus to 0 plus, and then it will decay. What we wish to find out is what will be the height under this condition. There is a small trick involved here. It is a slightly tricky problem because capital V goes to infinity, capital T goes to 0. So instead of capital V, let us use the quantity which remains a constant, which is capital V times T, which is equal to capital A, and therefore the maximum current, if I call that I max, when capital T tends to 0, well, first let us do it for general capital T. Therefore, capital V I write as A divided by RT, then 1 minus e to the power minus R capital T divided by L. All right. Now I expand this, expand the exponential, then I get A by RT. All right. What do I get inside the bracket? RT by L minus R square T square by L square 2 factorial plus and so on to infinity. Okay. This current, the maximum current, can therefore be simplified to the following: I max equal to, if I do away with the brackets, what I had was A by RT, RT by L minus R squared T squared by L squared 2 factorial plus etc. This I can write as A by L, the first term, minus A RT divided by factorial 2 L squared plus etc. And you see that when capital T goes to 0, the first term is unaffected, all others become 0, and therefore I max, which I shall call I of small I of 0 plus, which is equal to, let us say, I0, is given by simply A by L. And this is what was obtained earlier on the basis of the property of a delta function. Here we obtain this as a limiting case of pulse response, and therefore I of 0 plus is A by L, and when t greater than equal to 0 plus, the circuit goes back to its natural mode. In other words, we have R and L, where this current I at 0 plus is equal to I0, and therefore for time greater than 0, the current response shall be simply equal to I0 e to the power minus R T by L, which means that the current response would be, it rises to I0 and then simply goes to 0 exponentially. Is this point clear? This gives you a physical interpretation of the impulse function. What we did earlier was to obtain the impulse function as the limit of a pulse. What we have done now is to obtain the response to a pulse and then allow the pulse to become an impulse, and we see that the two responses are the same. This gives a physical interpretation to the question of impulse response. Now let us go to AC circuit analysis, and we shall start with the consideration of power. As you know, if we have an AC let's take a current generator. Let's take a current generator I of t is equal to root 2I cosine omega t, and let this current AC pass through a resistance R. Then the voltage across the resistance Vt shall be simply equal to root 2IR cosine omega t, and if we call IR, capital I is the root mean squared value or the effective value. If I call IR as V, then root 2V cosine omega t. The corresponding phasors are I 0 degree and V 0 degree. Alright. The power that is dissipated in the resistance obviously is a function of time, because both current and voltage are functions of time. So the instantaneous power P of t shall be equal to V times I, and you see that this is twice Vi cosine squared omega t. Alright, cosine squared omega t. In other words, the power is always positive. The power is always positive because it's the square of cosine, and the negative halves are also flipped into squares of the cosine, and therefore it makes sense to talk about the average power, capital P, the average power averaged over a complete cycle. Another notation for this P of t average, this average is over a cycle. In other words, it is 1 by t integral 0 to capital T or any other instant of time, t1, small t1 to t1 plus t. The only thing is it has to be one complete cycle, twice Vi cosine squared omega t dt. And you know the integral, the average value of cosine squared or sine squared over one period is half, and therefore the average power is simply equal to the product of the root mean squared values of the voltage and current. And you know the unit for this is watt. Vi, volts into amperes, it is watt. And therefore in an AC circuit, if there is a resistance and the current and voltage amplitudes are identified as root 2V and root 2I, the power, average power dissipated in the circuit is the product of the root mean squared values of voltage and current. And if you wish to find the total energy dissipated over a certain instant of time, all that you have to do is to multiply Vi by the time factor, and then we have what is known as watt second. The energy unit is watt second. The commercial unit is kWh, kilowatt hour. Now the situation changes if the voltage V and current I are not in phase. Suppose I is root 2 capital I cosine of omega t, and suppose small v is equal to root 2 capital V cosine of omega t plus theta, which may occur typically, let's say, in a situation in which a current I is allowed to pass through an impedance Z, where Z is magnitude Z, angle theta. It could be an inductive circuit, for example, resistance, inductance, or a capacitive circuit, resistance, capacitance, and so on. Then the voltage developed across the impedance and across the impedance shall either lead or lag the current I by some angle theta, which is indeed the angle of the impedance Z. Okay, you see the current and voltage phasors are I bar Z, and therefore the phase difference between V and I shall be the angle of Z, the impedance. And typically my voltage expression in the time domain shall look like this: root 2 V, where V, capital V obviously, is the product of capital I and magnitude of the impedance, Okay, now if this is the situation, then what is the power? The power, obviously, if you multiply V by I, small pt shall be equal to twice Vi cosine omega t and cosine omega t plus theta. Alright, and if you wish to find out the average value of this, then you have to integrate this over one period and divide by capital T. Before that, you recognize that twice cosine A cosine B can be written as cosine A minus B plus cosine A plus B. In other words, the instantaneous power in a situation where the circuit is not resistive, is not purely resistive, shall be given by Vi cosine of theta, the difference between the two, then plus Vi cosine of 2 omega t plus theta. Alright, cosine of A minus B, whether you take omega t minus theta or the other way around, it does not matter, because cosine of minus theta is equal to cosine of theta. Now if I take the average value of this over one period, you see the first term is a constant, so it does not matter. You are simply multiplying this by capital T and dividing by capital T, so this would be Vi cosine theta. On the other hand, the average value of a cosine over one period is equal to 0, and therefore the average value of small p is simply Vi cosine theta, and this represents the power dissipated in the circuit. You notice that the modification, that compared to a resistive circuit, it is still the product of V and I, volts into amperes, but it is also multiplied by cosine of the angle between the two phasors, the current and the voltage. And this quantity cosine theta, which is the ratio of P to the volt ampere product, is called the power factor of the circuit. Power factor of the circuit. Alright, the ratio of the power absorbed to the product of voltage and current is the power factor. Naturally, the power factor for a resistance, for a purely resistive circuit, is 1. Power factor for a purely inductive circuit is 0, because cosine 90 is 0. The angle difference between current and voltage phasors for a pure inductance is 90. And similarly, if a circuit is purely capacitive, again 0. And therefore power factor is non-zero only for a circuit which has a resistive component. If it is purely reactive, it is 0. Two kinds of power factor are distinguished. One is if the circuit is inductive. If the circuit is inductive, then who leads whom? If the circuit is inductive, voltage leads the current, and therefore the current lags the voltage. Alright, the current lags the voltage. This is the positive direction. This is the positive direction. The current goes in this direction compared to V phasor, and therefore the current lags the voltage in an inductive circuit. And in such situations, well, whether theta is positive or negative, power factor makes no difference, because cosine of minus theta is cosine theta. But in such situation, we say it is a lagging power factor. That is, the word lagging, it does not relate to power factor. It relates to the angle of the current with respect to the voltage. But the adjective lagging power factor is added if the circuit is inductive, and conversely the adjective leading is used for a capacitive circuit where the current leads the voltage. Alright, for a capacitive circuit the current leads the voltage, and we say in a capacitive circuit the power factor is leading. Alright. Now if you consider a purely inductive circuit, cosine theta is 0, purely inductive circuit, cosine theta is 0, and therefore power absorbed is 0. This does not, however, mean that energy for all times to come is 0. No. What it means will be shown by means of this figure. You don't have to draw it. It is there in the textbook. I have enlarged it to make things clear. The first we consider an inductance, a pure inductance. And suppose the current is as shown by this blue line. This is a current I equal to root 2 capital I sine or cosine? Sine omega t, because it starts from 0. Alright. The voltage across the inductance, which is VL equal to L di dt, does it lead or lag? It leads, and therefore its maximum is reached 1/4 of a period earlier, that is 90 degrees earlier. Alright. When omega t is less than the maximum of this by 90, the voltage reaches its maximum, because the voltage is 90 degrees ahead of the current, and therefore this curve, what color is it? Red. The red colored curve is that of the voltage across the inductance, and the instantaneous power is the product of the two, and therefore whenever the current and voltage are both positive or both negative, you see this portion, current and voltage are both negative, the power, instantaneous power, is positive. So it is positive here 1/4 of a cycle. The next quarter the current is positive, voltage is negative, and therefore the power is negative. Similarly, the next quarter the power is positive, and so on. Alright. Now what it means is, you see the power is also sinusoidal. The power is also sinusoidal with a frequency which is equal to twice the frequency of the current or voltage. Is that clear? The frequency is twice that of the current or voltage, which means that if I take average over one cycle of either current or voltage, or even half cycle, the average power is equal to 0. And that's all that it means by saying that capital P equals to 0. The average over one cycle or even half a cycle is 0. Alright. On the other hand, well, then we must have an interpretation. Before we conclude, we must have an interpretation of what it means when PL is positive. PL positive means energy is being stored in the magnetic field. PL positive means that the inductor takes power. It does not absorb it though. It does not dissipate. It stores it in its magnetic field. On the other hand, in the next quarter of a cycle, this quarter refers to the current or the voltage cycle, not the power cycle. Power cycle is half of the voltage cycle. Alright. So in the next quarter of a cycle, the power is negative, which means that the magnetic field is returning energy to the circuit. That is, the inductance no longer stores magnetic field, stores energy, no longer takes energy into its magnetic field. This energy that was stored is being given out, so that at the end of this again the energy becomes 0, and again it stores, again it returns, and this goes on. So the average power is equal to 0. The same story holds for a capacitance, except that the roles of current and voltage are reversed. In a capacitance, the voltage leads the current. So if this is the current, the blue curve, the red one is that of the voltage. You see, if the maximum occurs is that correct? The voltage across the capacitor, lags the current. Okay. So the current leads the voltage. Yes, that is true. The maximum current occurs before the maximum of the voltage. Alright, 90 degrees. And therefore, once again the same phenomenon occurs, that is when the current and voltage are negative, when the current and voltage are of opposite polarity, the power is negative. When the current and voltage are of the same polarity as here and also here, the power is positive. And when the power is positive, energy is being stored in the electric field, not the magnetic field. When the power is negative, energy is being returned to the circuit, and the sum total over an integral number of cycles is that the average power is equal to 0. If you interpret this in terms of this quantity Vi cosine theta, which is the power absorbed by a circuit, purely inductive circuit, purely capacitive circuit, the power absorbed is 0. But you see, the general expression for power absorbed is obtained by drawing the phasor diagram of voltage and current. Let us say we have arbitrarily, let's say this is the current phasor, and let's say this is the voltage phasor. Then the power is obtained by projecting one vector on the other. This angle is theta. It could be, in this case, the current is leading or lagging? Leading. So the power factor shall be a leading power factor, this angle theta, and you see the power absorbed by the circuit is given by the product of one of the phasors and the projection of the other phasor on the same line. That is, if you project I onto the direction of V, then the current in the direction of V is I cosine theta, and therefore Vi cosine theta is the power absorbed by the circuit. It could also be looked at from the another point of view, that it is I multiplied with the projection of V on the line on the direction of I. It's the same thing, because the projection is simply the magnitude of the quantity multiplied by cosine theta. And therefore one argues, what about the projection, the orthogonal projection? That is, what about the product Vi sine theta? Well, if this is I cosine theta, obviously there must be an I sine theta in this direction. All right. What about the product V and I sine theta? Well, this is because it is orthogonal, it can be represented by multiplication by j. This is 90 degrees away from Vi cosine theta, and this quantity Vi sine theta is called the reactive power, because it does not cause any absorption or dissipation of energy. In a reactance, power, average power is equal to 0, and this quantity is called the reactive power. Reactive power. Sometimes it's called VAR, that is volt ampere reactive, VAR. All right. For example, if it is 220 volt, 1 ampere, and theta is, let's say, 45 degrees, then you say 1 by root 2. So this is 220 divided by root 2, and the unit, we don't say it is watts. Actually the unit should be watts, but we don't say watts, because watts is reserved for the energy dissipated or absorbed, energy which cannot be recovered, which is lost. So this is not called watts, this is called 220 by root 2 VAR, volt ampere product, reactive, but multiplied by sine theta. And if you consider power as a complex quantity, now if you consider power as a phasor, voltage is a phasor, current is a phasor. If you consider power as a phasor, then obviously Vi cosine theta is its real part, and the real part is the part that is dissipated, that is irrecoverable from the circuit, and its imaginary part shall therefore be the VAR. All right, and therefore the power can also be considered as a complex quantity, and this is called complex power. Let's call this as, what do we say, PC, let's say, complex power. It's a phasor, and its real part is, we shall reserve the symbol capital P for this, plus j Vi sine theta, and this power, as you know, it is called a VAR, its unit is VAR, but it's also called an apparent power or reactive power. I think that is better. Let's call this the reactive power, Px. Okay, you will see that reactive power is of great importance in power, introduction to electrical machines, if you take that course, or power calculations, that is large power consumption and so on. However, in the case of electronic circuits, it is basically this power that we shall be concerned with, and therefore from now onwards we shall not make a reference to reactive power or complex power unless the context of the situation demands so. We next consider some circuits which are frequency sensitive. Is there any question on power? Any question on power? Okay. We next consider frequency sensitive circuits. When you put up an aerial on a simple 2-in-1 radio set to pick up the FM signal, for example, there are many signals which are being transmitted, which are in the air, many signals, and you tune a certain knob to pick up, let's say, Delhi FM or AM for that matter. All right. Now, what you basically do is different transmitting stations are transmitting at different frequencies, and what you basically do is, this is the aerial, basically do is you have an inductance capacitance circuit in parallel, L and C, and tuning, what you are doing essentially is rotating a capacitor knob, so you are varying the capacitance. Now you see that the impedance of this circuit is j omega L multiplied by 1 by j omega C divided by j omega L plus 1 over j omega C, which is equal to j omega L divided by 1 minus omega squared LC. And you see that at the frequency omega 0 equal to 1 over square root LC, the impedance becomes infinite. Now, impedance becomes infinite means what? That this particular frequency shall be picked up by the circuit. This impedance is infinite, and therefore any small current, actually in practice it cannot be infinite, it is very high. So any small current flowing at that frequency shall be dropped across here, and all other frequencies shall find an easy path to ground. It is only at this frequency that the impedance has become very large. All other frequencies find an easy path to ground, and therefore the current that is picked up, well, you can consider this to be infinity, no problem. The current that is picked up at this frequency cannot pass to ground, it must pass to the receiver. All right, this is the simple tuning circuit of a radio. Is that clear? So what does this LC, these two parameters do? They perform a frequency sensitive job. That is, they pick up a certain frequency, and the combination of resistance inductance, the combination of resistance capacitance, or the combination of inductance capacitance, or a combination of these three elements can perform frequency sensitive jobs. For example, if you wish to pass the low frequencies in a circuit and cut off high frequencies, for example in base control, what you do is basically allow the high frequencies to be rejected, you admit only the low frequencies. Or in the case of a power supply, you have two diodes, a transformer and a rectifier circuit, which produces, the full wave rectifier produces something like this. What you wish to do is to retain the DC and reject all the alternating components, and therefore you require what is known as a low pass filter. Low pass filter. A low pass filter is one which passes low frequencies and rejects high frequencies. In a similar manner, a high pass filter HPF is one which passes high frequencies but rejects low frequencies. Alright, high pass filter. A band pass filter is one which rejects low as well as high frequencies. BPF is one which rejects both low and high frequencies. If I plot its transfer characteristic, it would be something like this. It rejects both, if this is frequency, it rejects both low frequencies and high frequencies and passes a certain band of frequency. That's why it is called a band pass filter. Similarly, you can have band stop filter like this. It passes low frequencies, it rejects a band of frequencies, and then it passes high frequencies. So this is called a band stop filter, BSF. And we shall look at some of the elementary filters that one can think of with a very specific purpose. We shall consider a few practical examples of such filters. Let's look at two very simple circuits. One is, let's say, an inductance in series with a resistance. Please be with me. And let's say this is a voltage phasor V whose frequency omega is variable. Frequency omega, for example, this could be a typical signal generator that is available in the laboratory. Its frequency is variable. I want to find out, let's say this is VI phasor, input voltage, this is sinusoidal of a frequency omega which you keep on varying, and the output is V0, and let the phasor be V0. Then you see V0 over Vi would be simply, phasors can be treated in exactly the same manner as DC voltages, and therefore this would be R divided by R plus J omega L. Alright, this is the transfer function. A transfer function is the ratio of the desired quantity to the source quantity or the excitation. It could be current to voltage ratio, or voltage to voltage ratio, or voltage to current ratio, or current to current ratio. Alright, so this is the expression for the voltage transfer function. The voltage is being transferred from this terminal to these two terminals. Alright, so it is the voltage transfer function. Is this term clear? Voltage transfer function is being transferred from one point to another, and what we want to do at the output, we used to retain certain frequencies and reject others. Now if you look at this expression, this is equal to, I can write this as 1 plus J omega L by R. Alright, let R by L be equal to omega 0. Define the quantity R by L as omega 0. Then you can write for this circuit V0 by Vi, the ratio of the two phasors, as equal to 1 by 1 plus J omega by omega 0. Alright, is that clear? What we had was 1 by 1 plus J omega L by R, and R by L has been designated as omega 0, so I can write this as omega by omega 0. It is as if the frequency is being normalized with respect to the fixed frequency omega 0. Omega 0 is fixed because omega 0 has been defined as R by L, which are the parameters of the circuit. Okay, and therefore the magnitude of this phasor ratio is given by 1 by square root of 1 plus omega by omega 0 squared. Alright, and the angle is minus tan inverse omega by omega 0. Is this clear? Is this okay? Or have I gone too fast? It's okay. Now, if I plot this, if I plot the magnitude, I can write this as m angle theta. If I plot m, the magnitude versus omega, you see at omega equal to 0, it would be 1, and then as omega increases, it would gradually fall like this. Is that clear? Okay. As omega increases, the denominator increases, so the curve gradually falls like this. What happens when omega equal to omega 0? What would be the magnitude? 1 by root 2, which is 0.707, all right, 1 by root 2. So the voltage output, let's look at the circuit now. At DC, at omega equal to 0, the ratio of the two quantities, magnitudes, is 1, which is quite amenable to reason, because at DC, this L behaves as a short circuit. So the total voltage is dropped across R. Agreed? So the voltage across R is the same as the input voltage, or the ratio is 1. Now, when the ratio is 1, what is the power? V squared by R. Alright? So input voltage magnitude squared divided by R. On the other hand, when the output voltage falls to 0.707 of the input voltage, what is the power in the resistor? Half of the power at DC, that is the power in the resistor. Power in the resistor is magnitude V0 square divided by R. Alright, the phasor V0, you take the magnitude, square it and divide by R. Now this was equal to input voltage at omega equal to 0. At omega equal to omega 0, the voltage magnitude has fallen by 1 by root 2. So the power now has become half of the power at DC, and therefore omega 0 is given the name of half power frequency. Half power frequency, or in popular parlance it is called the cutoff frequency. Cutoff frequency. It is as if the circuit behaves as a filter, retaining frequencies from 0 to omega 0 and rejecting from omega 0 to infinity. Therefore this circuit is a low pass filter, because it favors low frequencies as compared to high frequencies. So it is a low pass filter. Is that clear? Suppose I interchange the two. Suppose I interchange the resistance and inductance. That is, I take no, it's the other way around. I take the resistance and the inductance, and this is my VI, this is my V0. What kind of a filtering do you expect? DC, at DC this is short. So if you plot V0 by Vi mod, it will start from 0. At DC it is 0, and when the frequency increases, the impedance of this increases, and therefore the ratio of the voltage increases, and at infinite frequency, when this becomes Z of S at S equal to infinity, it becomes open, and therefore I shall get this will rise to 1 at infinite frequency. Alright, and once again you can define a half power frequency as the frequency at which the ratio of the two voltages becomes 0.707. This would be omega 0, and we say this is a high pass filter with a half power frequency of omega 0 or cutoff frequency of omega 0. It does not take very long to show that the circuit containing a capacitor and a resistance, what kind of a circuit is this? It is also a high pass filter, and I can write down the ratio of V0 to Vi as equal to, yes, R divided by R plus 1 over j omega c, and this can be written as 1 divided by 1 plus 1 over j omega cr, and if I write 1 by cr has the dimension of frequency. If I define this as omega 0, then my ratio of the two voltages V0 to Vi becomes equal to 1 by 1 minus j omega 0 divided by omega, and so the magnitude becomes square root of 1 plus omega 0 by omega whole squared, and the angle becomes tan inverse, yes, plus or minus, plus omega 0 divided by omega. Now you see that when omega is 0, the magnitude is 0. When omega is 0, this becomes infinity, 1 by infinity becomes 0, and the angle becomes pi by 2. On the other hand, when omega increases, the magnitude increases and reaches the value 1 at infinite frequency. When small omega is infinity, the value is 1, and therefore this also behaves as a high pass filter. Now if I take the frequency omega 0, at omega 0 the value of the magnitude is 1 by root 2, and therefore the power in the resistor becomes half of the power at which frequency? Infinity, not omega equal to 0. Omega equal to 0, the power is 0. So the power at omega equal to omega 0 becomes half of the power at infinite frequency. All right, and the angle, what is the angle at this point, at this frequency? Pi by 4. Omega, therefore this is a high pass filter with a cutoff frequency of omega 0 equal to 1 by CR. All right, we shall look into some applications of low pass and high pass filters next time. Is the next time Friday? Friday is a holiday, so Monday. Monday is 28. Monday is 28. Okay, I may not be able to take my class on Monday, but I shall notify this on my door by day after tomorrow. When does the mid-semester break start? Is it mid-semester break? No. Students' week. When does it start? This Friday. Thursday. Okay, Thursday morning I will notify on my door if the class will be held or not. Okay.